Good afternoon. We are going to discuss the societal applications of radiation. First, I would like to thank AERB for inviting me to take part in the celebrations of Azadi Ka Amrit Mahotsav. Before I start, I must confess that I may not be able to do full justice to the task assigned to me for two reasons. The first reason is that there are so many societal applications of radiation that in the time assigned to me, I may not be able to cover more than 10 to 20% of the various applications. The second reason is that I am not going to find it easy to match up to the communication skills of Mr. Malhotra. I am not going to try, so I am going to be relaxed for the next few minutes. Now, I am going to assume that you may not be familiar with most of the applications I am going to discuss, so you will forgive me if you find it too elementary. When we are asked to talk about radiation, there are many questions that we have to answer. Now, primarily, I would like to acknowledge the fact that I have taken many illustrations in this presentation from IAEA materials and from other sources. I am grateful to the sources. When you have to talk about radiation, it's first question that anyone asks is what is radiation? So it's emission of energy. It's a simple answer, technically correct. An emission may be plain energy, as in the case of an X-ray machine. We are all familiar with it. This energy is emitted from the machine. Emission may be an energetic particle originating from a radioactive material. There I go. What is radioactive material? Any material that emits radiation, any material that is radioactive is a radioactive material. A radioactive material emits a particle. Sometimes this particle may be accompanied by plain energy. This is a radioactive material that is emitting a positively charged particle. We call it alpha. Here is another radioactive material that is emitting a negatively charged particle. We call it beta. Sometimes it can be accompanied by plain energy. We call it gamma. Sometimes we have radioactive materials which emit a particle which carry no charge, a neutron. So with these two slides, with these premises, I think our understanding of what is radiation and what is radioactive material is all that is required for us to continue with the discussion. Now, radioactive materials in some circumstances are referred to as radioisotopes and sources. So I'll be using these terms for my convenience. There are two types of radiation that we hear about. One is non-ionizing radiation, like visible light, radio waves, the waves that help us communicate through our mobile phones, microwaves. These are all non-ionizing radiations because they don't carry enough energy to cause ionization. As you know, ionization is a process of removing an electron from an atom. They don't carry enough energy to do that. The other kind of radiation is ionizing radiation used in medicine, industry, power production, everything. And this is the subject of our discussion. They can cause ionization. We're going to see how we take advantage of this property. Now, uses of radiation are many. Radiation is used in industry, medicine and research, and nuclear power production. So you see each of these in some detail in the slides that follow for healthcare and medical applications. In medical applications, there are two aspects, diagnosis and therapy. X-ray exam, this is the best known example of application of radiation. We have seen it. And we also have recently CT scan technology. Whereas an X-ray gives a two-dimensional picture of a person's tissue under investigation, a CT scan looks at the area of interest and cuts it into slices so you know exactly where the interest is, where the concern is. That is the advantage of CT scan. And there are globally 400 crore diagnostic procedures per year which are in progress. By the time I complete the presentation, I add a few lakhs. Now, continuing with medical diagnosis, one was X-ray and CT scan. Another modality is nuclear medicine. some chemical compound will make use of this fact. Some chemical compounds seek specific organs, like in this case, iodine, when consumed, concentrates preferentially in the thyroid. So there are many such radioisotopes which seek certain particular organs, specific organs of the human body. A radioisotope is administered to a patient either orally or through injection to study the functioning of specific organs in the body, like could be heart, could be lungs, could be brain, liver, kidneys, bones, whatever. So the appropriately labeled radioisotope is given to the patient, and after reaching the target organ, when I say target organ, I mean the organ that the isotope is going to seek. As we saw in the case of iodine, thyroid is a target organ. So after reaching the target organ, the radioisotope reveals information about the organ. This is the principle of nuclear medicine. Globally, several lakhs of nuclear medicine diagnostic procedures are carried every year. Now you may ask, in the case of X-rays and CT scan, radiation simply passes through the patient's body and leaves the body, and on the way leaves the message in the X-ray, in the film. In the case of nuclear medicine, we are administering radioactive material. We are giving radioactive material and putting it inside the body of the patient. So is that an advantage? Is that a disadvantage? I'll tell you the great advantages of nuclear medicine. The doctor, by giving a small quantity of radioisotope, he is able to get a clear picture of the functioning of an organ inside the body. The quantity of radioactive material given is very, very small. They have a short half-life. They don't give any significant radiation dose to the patient. If at all, only the patient gets, and a small quantity of dose. Now, diagnosis by nuclear medicine procedure is more accurate as compared to the conventional methods of making diagnosis. It is faster. The patient is administered the radioisotope. Within a few hours, you get a complete picture. You find out what you wanted to find out. The information you get is accurate, and no surgery is involved. It's non-intrusive, and it is painless to the patient, and it is cost-effective. Considering the accuracy of that diagnosis, it is cost-effective. Anybody who knows about healthcare will agree that proper diagnosis is half the task. If the diagnosis is not done well, the patient is going to continue to suffer. If diagnosis is perfect, the patient has a chance of getting cured. So all these advantages are offered by nuclear medicine. Cancer can be detected through nuclear medicine. Even children can undergo these procedures because the dose they will get will be insignificant. So these are the many advantages of nuclear medicine. We spoke about diagnosis till now, X-rays, nuclear medicine. Now we come to therapy. It's known that high doses of radiation can destroy cancer cells. Now some cancer cells can be preferably treated by nuclear medicine procedures. For example, cancer of thyroid. By administering appropriate radioisotope in appropriate quantities, cancer of thyroid can be addressed. Now, cancer can be treated by external beams or by placing the source at the tumor site. We will see examples in the next slides. Many types of cancer can be treated by radiation as a preferential mode of treatment. Nearly 1 crore radiation therapy treatments per year are being carried out today. Now, I spoke about external beam therapy. Here, as you can see, the cancer suffering patient is lying on the couch. There is a radioactive source inside the machine. The source does not come out. The source is inside, and it is emitting radiation, in this case gamma radiation. A narrow beam of radiation is directed towards the tumor site, and that is delivering the desired dose to the patient. This is external beam therapy. In some cases, the source itself is placed at the tumor site for a short period of time. The dose is delivered to the tumor and the source is withdrawn. This is brachytherapy. So We saw about medical applications of radiation, diagnosis and therapy. We go to the next application, agriculture research and preservation of food. In agriculture, we know that plants get the nutrients from the soil. To study how well the plants take up nutrients, radioactive material is mixed in the soil, say phosphorus 32, sulfur 35, depending upon what the researcher is seeking, is mixed with the soil, and then radioactivity is measured in the parts of the plant, like leaves, stems. You take it out and measure the radioactivity present there. The radioactivity that is measured in parts of the plant indicate the efficiency of uptake of nutrients by the plant. Similarly, study of uptake of fertilizers can be done by adding radioisotope to the fertilizer, and this study will help to enhance the agricultural output. And preservation of food, as we saw in the earlier talk, is a vital application of radiation. Now, large quantities of food grains, vegetables, spices, etc. are wasted due to infestation. Some germs are present on all these food items. They multiply, they won't be visible. After a while, you'll find that all these things are wasted. These food items are wasted. Now, radiation can kill the germs, and radiation thereby protect the food against infestation. This is a very valuable societal application of radiation. To continue, a lot of food is wasted due to spoilage. It's not fit to consume. So if you do this food irradiation, that wastage is protected. So when we irradiate food, we don't expose the food directly to radiation. We expose them to radiation in a packaged condition. Gets irradiated, the radiation passes through the package, radiation reaches the vegetables, kills the germs, and disinfects them. Now, what is the advantage in exposing food in packaged condition? There is no touching after radiation. After radiation, even if we handle the package, you're only touching the package, you're not touching the food item which you're protecting. Therefore, there is no risk of reinfection. So what is the point in sterilizing food and then transferring infection by touching it after this? We can do it in a packaged condition. The package does not interfere with the efficacy of irradiation process. Now, to continue this preservation of food, certain harmful organisms which are present in food can lead to spoilage, wastage of food, and they can be inactivated. And this will, but sometimes you can even extend the ripening period. In this case, mango. Mango exporting countries like India have a lot to gain with this technology. If you send mango from India to United States, it may take 3 days, 4 days to reach. By that time, it will be spoiled. You expose them to radiation, you slow down the ripening process, so when it reaches there, it will be right. Now, with all this, we are able to extend the shelf life of food items considerably. Now, we have come across instances of foods developing sprouts. Particularly, you might have seen potatoes, onions, etc., which we buy in large quantities, kept in the house. They develop sprouts. If they are exposed to radiation and they reach the market, sprouting will not happen. Like we have this proton facility where this is done. They expose potato and onion, preferably now other items also. Now, exposing these items to radiation inhibits sprouting and makes the food consumable, extends the shelf life of these food items. Now we saw medical applications, agriculture applications, food preservation. We come to sterilization of medical supplies. Single-use medical supplies like syringes, gloves, cotton wool, bandages, which are used in operation theaters, they can be sterilized by exposing them to radiation. Currently, there are many methods of sterilizing them, like autoclaving and all that. They are effective, all right, but after a few hours, all these items start getting reinfected. So the effect of sterilization decays after a few hours, whereas in the case of items which have been sterilized by radiation, they remain sterile for pretty long periods of time, thereby increasing use of these single-use medical supplies. Another area where radiation finds application is blood irradiation. There are many cases where after blood transfusion is completed, the patient who received blood rejects blood. Now, you know that blood transfusion is resorted to as an important life-saving activity. If the patient rejects the blood, then the whole operation fails. You'll have to run around, get a fresh supply, hoping that that will not be rejected. Now, this rejection takes place because of some immunological reaction on the part of the patient. Now, this immunological reaction can be inhibited by exposing blood to radiation. By giving blood samples a specified amount of radiation dose, you can make sure that this rejection of blood will not take place, thereby making blood irradiation a boon to life-saving blood transfusion operations. It's a very important technology. In India, we are able to practice it. Many hospitals, many places have come up where they're doing this blood irradiation. So next we come to industry. There are many applications, and we'll see maybe the most important of those applications. Industrial radiography. This, as you know, is like taking an X-ray of a human being. This detects defects in welds and metal casting. This picture will make it clear. We have an object here, a steel plate, let us say thick steel plate. It may have some blowholes, it may have some faults within the plate which will not be visible to the naked eye. And in this condition, this metal plate cannot be used. It can't be a part of a boiler. You will understand. Internal pressure can make it weak and blow up and cause loss of life and loss of property. So we can't use it. So how do you find out whether the plate is good enough or not? Expose it to radiation. Keep a fresh film that will receive radiation, and as you can see on the right extreme, you will find that developed film where you will find this pattern. Wherever there is a hole, let's say, there is less material, therefore radiation would easily pass through, so cause more blackening. In places where there is no defect, radiation had to pass through the metal plate. It was absorbed. Only what was transparent was allowed. This picture tells you whether there is a fault, how many faults are there, etc. So this will help people accept or reject this plate. This is easily the best known industrial application of radiation. This is very much in practice. From the earliest days, this practice has been going on in India, maybe for nearly 100 years. Since 1925, I believe, we have been doing industrial radiography in India. Now, in industrial process control, sources play a very important role. I'll give examples. This is a schematic diagram of a thickness gauge. So there is a sheet material. You want to make sure that the thickness of this material is uniform. To ensure that, what you do is you keep a source here at the bottom and you keep a detector here on top. Radiation passes through this sheet and detector knows, okay, if this is the appropriate thickness, this will be the radiation that will come out, so this reading will tell you. Now, if the thickness is not enough, then more radiation will come out and that will be seen by the detector. If the thickness is extra, more than what you desire, then more absorption will take place in this region and will say less radiation, and this detector will tell you. So thickness of thin layer of metal sheet can be measured using this technology to assure that the thickness of the product is uniform. So that is it's an important industrial application. It's a thickness gauge. Here, film thickness can be seen to be uniform, and we have in paper industry. This is a great boom to all of us, to you and me. The early days when we are not sure of the thickness of the paper, the photocopying machine, the Xerox machine, we had the problem of paper getting stuck. So some papers had appropriate thickness, some had less thickness, some had more thickness. In the early days, we had a problem. If the paper was not thick enough, sometimes 2 sheets of paper will come through the printer. My printer would be affected midway. So I had to open the printer, remove the papers and start all over again. Or if the paper is too thick, it will enter the printer easily. Midway, that will also get stuck. So thickness of the paper has to be uniform, has to be appropriate. This is ensured by this technology. Now we have these level gauges which are widely used in process industry, where you want to ensure that the fluid level in a column does not fall below a certain level. Let us say that in this application, you want to ensure that the radiation level stays, say, somewhat around this level. You don't want it to fall below this level. So you have kept the radiation source here. Radiation is coming out, and there is a detector here. So long as there is this fluid in the path, this detector will say only a certain amount of radiation dose. If the level falls below this, then there will be nothing to stop radiation. So the radiation will simply pass through this empty space and seen by the detector. So the detector will say, well, there is no fluid here. So the operating engineer will do the necessary thing and make sure that the level is made appropriate. And this is a very well-known application, the beverage filling level. This is commonly used in many countries, used in India also. There are cans, maybe they are used for containing Coca-Cola, Pepsi, beer, whatever. The filling level has to be appropriate. And there is a source here, weak source, typically americium 241 source, and there is a detector on the opposite side. So from the fact that the radiation is passing through the beverage, the detector is happy. If the filling level is low, you'll see more radiation. Filling is not enough, so that can will be rejected. So this is another example of a level gauge. We have many density gauges which are used in construction industry, road construction, bridge construction, etc. This density gauge also finds application in exploration of oil and gas. Here at this end you have a probe which contains a cesium-137 source, which is used as a density gauge. It also contains a neutron source. The geologists want to know what is the density of the soil there. They want to know if there is moisture present there. This information will help them decide whether they can go ahead and dig deeper and collect oil, whether it is worth taking all the trouble. Is it economically viable? To make that decision, they would like to know what is the density of the soil here and what is the moisture content. So for that, what they do is the density is determined by the source density gauge, which emits radiation. If the density is high, it will be reflected. There are many atoms to reflect. If the density is low, there are not many reflectors, so the reflected radiation will be low in intensity. So from the intensity of the reflected beam, they'll find out about the density of the soil, and the neutron source will interact with the moisture around. When neutron, as you know, when neutron interacts with moisture, it loses energy. So neutron with reduced energy will come back. So when the neutron's reduced energy is seen, you know that, okay, there is moisture. If there is no moisture, they won't lose their energy. They'll continue to go. So this will give information to the geologists to decide whether to go ahead or not. This is another important application of radiation. You see, in coal industry, when they dig out coal and sell it, all these power stations, thermal power stations, they buy them in tons. But coal may contain a high quantity of ash. There is some silicon oxide and such materials. Their density is high and they have practically no calorific value. You can't burn them. They give no energy. You're only paying for the kilogram value and wasting it. That's the ash content. So you want to make sure that the ash content in the coal that you buy is minimal. For that purpose, this is what they do. There is a conveyor belt. It's a cross section, vertical cross section. So there is radiation which passes through this belt. Then if there is this ash item, if there is a high density item, that will stop the radiation. So by using a sensitive detector on the other side, you will know how much ash content is present in this coal, so that you can decide whether you accept this campaign or reject this campaign. This is an important and popular use of density gauge. Now, there are many more gauges. We can't discuss all of them for paucity of time. I'll give one example of radiotracers. Many examples of radiotracers. I'm mentioning possibly the most obvious. You see, pipelines are cross-country pipelines are laid like this. After this is complete, they will cover it with mud, so it will not be visible. So fluid can move through this pipeline. It's an inexpensive, efficient way of transporting fluids. But sometimes a leakage can occur. When the leakage occurs, it will be discovered by the arrival of smaller quantity of the fluid at the desired place. But where exactly is the leakage occurring? It will run to several kilometers. One can't dig up everywhere. So what they do is, you inject radioisotope at one end, and you know that along with the fluid, the radioisotope will move. Keep tracking it. At one point where leakage occurs, the radioactive isotope also will leak out, and the radiation will be higher. Dig only that place and then repair the pipeline. You can continue with this. So there are many applications of this radiotracer technology. Now I come to consumer products. Here also there are many examples. I'll probably deal with 3 or 4. We have this smoke detectors. Even in this hall we have many smoke detectors. Millions of the smoke detectors are doing a wonderful job. Earlier on we had fire detectors. The principle was, as the temperature increased, the increase in temperature was sensed by the instrument and they'll give a warning. But by that time that it's able to detect increase in temperature, a lot of damage would be on the way. So still they could save as many people as possible, as much property as possible, but there would be losses. But smoke detector, you don't wait for the temperatures to rise. Even smoke will be detected by this. You're using a very sensitive detector together with the radiation source. So this is being used all over the world. Several billion smoke detectors are operating, saving lives and property. And this dial painting, the principle is simply that there are certain chemicals which have an interesting property. When radiation is incident on those compounds, they absorb the energy of the radiation and emit them back. When they emit this energy back, it is emitted as light. They are called radioluminescent compounds. We are using them in dials. This kind of dials, there are a variety of dials. They can be used in the field. Supposing a dial like this being handled by the defense personnel, and they're out in the darkness, they don't want to switch on light and see what the dial is reading. Or there won't be power supply in the field in the darkness, but this will give them the information that they need. And this exit gate, it's a very interesting and highly useful application. Imagine we are sitting in a theater or a hall or some such place, and then suddenly there's a power failure or there's a fire accident and there's a power failure. We have to leave the hall. And how do you know where the exit door is? If you don't know where the exit door is, there will be a stampede. You know, stampede can be dangerous, more dangerous. It can kill nearly as many people as fire can kill. So we need an indication to say, look, this is the exit gate. Go to the gate, you can leave the room. But even this will fail if there's a power failure. So you want an exit board which will show you even if there is no power. For that purpose, we make use of this radioluminescent compounds. There is always radiation coming out of it. This compound is going to absorb the radiation, emit energy. So you know that this is the exit gate, and this can save many persons from getting affected by stampedes. Now, radioactive thorium is used in fluorescent lamps to improve efficiency at low cost in all these tube lights. We have little quantity of thorium as starters. They make sure that the light emission comes out earlier than otherwise. And we also have this example of Petromax lamps using thorium in this gas mantle. Now, this is a gas mantle. You know, the white stuff that looks like a bulb. It's actually made up of nylon net. It is soaked in a thorium compound, and thorium ensure that the light you get out of it is brighter. There are many such applications used in India, many parts of Asia, and almost all over Africa, and many parts of Latin America, if I'm right. So this is a very useful application of radiation. Now, consumer products done, we go to security. In baggage check, We have seen it in airports and some hotels, malls, cinemas, etc. So these X-ray units that are used for this purpose, they are very precise. They give accurate information. They can detect contraband items and substances even if they are present in very small quantities. So they ensure security of the place. And cargo inspection is a very important application. Again, we had to make sure at the customs that these boxes do not carry any contraband item. This container will have a large number of boxes. So in the olden days, the customs officials will take them away to another place. They will open the container, take out the boxes and see what they contain. Whether it was done at random or in every case, this was not convenient and it was not efficient. Now there is an X-ray machine on one side, there is a detector on the other side, and this detector there is a monitor. That monitor tells you what exactly is contained within this container boxes. They can give you a lot of information about the shape of the content, density of the content, and even the composition of the content within these boxes. So this arrangement makes use of commercially available radiation sources like high energy X-ray sources. In some cases, even radioactive sources can be used. And the efficiency is that a truck can pass through. You don't have to stop the truck in every case. In many cases, you can allow the truck to drive slowly in front of this frame and you get the information you need. So they are very efficient and they are very effective, and they are important in ensuring that contraband items do not enter the country. Imaging is fast, it doesn't take a long time, it's almost instantaneous, and cost of operation is relatively low. So in many border crossings, not only India, all over the world, they're switching over to this radiation monitoring for cargo inspection. Now comes probably a very important part, application of radiation. Uranium-235 is a radioactive material. Uranium is a fuel for nuclear power. It is used in nuclear power plants. It undergoes nuclear fission, nuclear reaction, as you know, releases energy as heat. Heat is used to boil water. Water produces steam, and pressurized steam turns turbines and power is produced. Now, what are the advantages of nuclear power? The fossil fuel in this world is depleting. It may not last many decades. We're definitely going to be out of these fossil fuels, whereas the world has a huge stock of nuclear fuel. So we can be assured of power for a long time if we use nuclear fuel. And there is no carbon emission. As Mr. Malhotra said, there is no carbon emission. So you are getting clean energy. And the byproducts, when you operate a nuclear reactor, they are radioactive sources, and they can be used, as you know, in medicine, in industry, in agriculture and research, and so many other purposes. In some reactors, the byproduct can be the fuel for the next generation if it is a breeder reactor. There are many advantages of nuclear power. Because it is very well known to all of you, I'm saying only that much about nuclear reactors, and there are some more applications of radiation. We'll concentrate on research and investigation. Carbon dating is a very well-known process. The principle is this: carbon-14 is a radioactive nuclide. It is present in all organisms, you, me, the tower, tree, everything. Now, carbon-14 decays, quantity comes down due to radioactive decay. It has a half-life about 5,700 years. And in a living organism, it is replenished. We make sure that the ratio of carbon-14 to the non-radioactive carbon is maintained at a fixed level. This is a ratio of C14 divided by non-radioactive carbon. It's maintained, it's fixed in all living beings. Now, if an organism ceases to live, what will happen? C14 will continue to decay, nothing to stop it. It will continue to decay. But there is nothing to replenish because it is not living, there won't be any replenishment. So the result will be that the ratio of C14 to non-radioactive carbon that will slowly reduce. So this reduction in this proportion of C14 in the sample will reveal when the replenishment stopped. That is the age of the objective. That is the age of the organism that we are considering. Now, carbon dating can be used to find when this dinosaur existed. If you give a piece of its bone, one can find the age of any of organic materials, whether it be a tree or a leaf or an organic relic of Jurassic era. These are some of the great advantages of carbon dating. Carbon dating was indeed used to estimate the age of the Shroud of Turin. You might have heard about it. It's something very sacred for Christians. It's a cloth which was discovered a few hundred years ago. It was believed to be the shroud that was used to cover Jesus Christ, and they're trying to find out the age of this. Carbon dating helped in this. It was also used to find the age of the Jewish sacrament, the Dead Sea Scrolls, and this were found out last century. They found out whether they indeed belong to the era when it was believed to have been written. These scrolls were written over a period of 200 years, more than that. So they could find out, okay, this piece was written in the 2nd century BC. This piece was written in the 1st century BC. This piece was written in the year 63 AD. To such precision, they were able to establish the age of this scroll. So the carbon dating is a very valuable and interesting application of radiation. Now we come to neutron activation analysis. I'm sure all of you know about it. Just to give you a brief introduction, consider this object. And there is some impurity in this object. I don't know how much impurity is there. I don't know whether the impurity is there or not. But I have this object. I want to investigate. The first thing I do is I expose it to neutrons. And I know that neutron can make non-radioactive object radioactive. So this is called activation. Now after this, the object itself may get radioactive. Even the impurities I am looking for, they will also get radioactive. They start emitting radiation. So radiation emitted by various atoms, they carry the signature of the emitter. Looking at the radiation, you know, okay, it is coming from cobalt-60. It is coming from cesium-137. It is coming from whatever isotope it is. So looking at this radiation, you can find out, okay, this impurity is present. It is present in this much quantity. So this is the basis of neutron activation analysis. But how is it applied? Let's see. It is applied in archaeology. You found an old pottery and you subject it to activation. And you found that this contained silicon, manganese, and iron. That means this was used to carbon dating. You find out the age of this pottery. Then during using this neutron activation analysis, you know that at that time they had technology of using silicon, manganese, and iron, etc. That is the advantage. And second, criminal investigation. Even items like small pieces of glass, gunpowder, poisons, whether they're present at the crime site, can be found using this neutron activation analysis. Now I'll give an example of forgery detection. The next two examples are very well known in Europe, and we know about it because we have theoretical knowledge. This forgery detection, I'm sure all of you recognize this portrait. This is called Girl with Pearl Earrings. It was painted by a Dutch painter, Vermeer, Johannes Vermeer, that was his name. He lived in the 17th century. Now, a good artist among us can create an identical picture. Use the same size, same colors. You can take it to the market and say this is a replica made by Vermeer himself. And a person who sees no difference between them will happily give a huge price, will accept it. But before buying, he would do an activation analysis. And that activation will say, okay, this contains certain compounds. And look at the radiation, I find the presence of certain compounds in paints which are not available in the 17th century. Only the 20th century, these points came to the market. So this is a forgery. So this kind of This technology has been used to discover many such forgeries in Europe. Now there is one more example, that is forensic science. You recognize this gentleman? Napoleon Bonaparte. He died in the prison of St. Helena in the year 1821. At that time, it was suspected that he died of arsenic poisoning. There was no reliable way of determining whether he died of arsenic poisoning or not. But it was confirmed in 1960. How did they do it? If arsenic is given to a person, it directly goes to the hair. In fact, arsenic 76 was used for brain scanning in nuclear medicine some years ago. Now, arsenic 76 will go and seek the hair. They settle there. Any arsenic, non-radioactive arsenic. What was given to him was non-radioactive arsenic only. And then what they did was they collected a few strands of hair of Napoleon Bonaparte. They exposed it to radiation, exposed it to neutron radiation, and the activation results showed that there was arsenic 76. Arsenic 76 was seen because it was arsenic 75 inside. Non-radioactive arsenic was present in the hair of the person. So they confirmed in 1960 that he died of arsenic poisoning in the year 1821. So there are many such interesting and useful examples of neutron activation analysis. This is a subject in itself. I'll need more than 2 hours to give examples of it. There are many more societal applications of radiation. So I'm leaving the application at this point, but spend a little time on safety. When we work with radiation, we must be careful and safe. Is there any biological effect associated with radiation? Yes, we know. There are basically two types of biological effects. One is probabilistic effect, also known as stochastic effect. The examples of probabilistic effect are cancer, leukemia, genetic effect, etc. This probabilistic effect is characterized by the fact that as the dose increases, the probability of the effect increases. If you want to make sure the probability of an effect is zero, what should I do? I mean, make sure that the person receives zero dose. I'll ask you a question, we'll find an answer soon. Is it possible to ensure that a person gets zero dose? We'll come back to the answer shortly. The other effect is deterministic effect, which is characterized by a threshold dose. Some examples are cataract, infertility, skin burn, etc. Now, the meaning of this threshold dose, the significance of this threshold dose is that unless a certain dose is given, the effect will not appear. Yes, we can be sure it will not appear. If the threshold dose is exceeded, then this effect will appear. If you far exceed the threshold dose, the severity will be more. Now, from this information, we can safely conclude that probabilistic effect is minimizable. You can make it zero if you can make the dose to be zero, but appears to be minimizable by making sure that you get less and less dose. And deterministic effect is preventable. Make sure that any person working with radiation doesn't receive any dose which is recognized as a threshold dose. So with this knowledge, we look at how we work with radiation. There is a system of radiation protection which has 3 components. Logical. First is justification of practice. That is, if there is benefit from the radiation, look, is there any risk, is there any harm from this practice? If the benefit outweighs the risk, then okay, this is a justified practice. Now, second is optimization of protection. We talk of optimization of protection because there is little cost involved in achieving protection. We want to make sure that there is some cost optimization to be done. Why should it be done? If we insist on a very high level of protection to make sure and involving huge cost of protection, therefore huge cost of production itself, then this technology may not survive. You can ensure, for example, that there are no road accidents by making a rule that the speed limit I'll allow is 0 miles, 0 kilometers per hour. Thereby you're just killing the technology. A patient cannot be rushed to a hospital because you reduce the speed limit to 0. So technology offers you a lot of benefit. Make sure that they maximize the benefit and minimize the risk. So optimization is going to help you in this. Even when you do this optimization, make sure that an ultimate dose limit is never exceeded. You specify a dose limit so long as you make sure that your optimization respects this dose limit. Yes, we are on track. So this is a 3-element description of system of radiation protection. Dose limit in any case should never be exceeded. This is ultimate. We'll come back to dose limits now. Now, the aim of dose limits, I'm not going to give the numbers, you can find them in any textbooks. Aim of dose limit is to prevent deterministic effect. We saw it was possible because fortunately we have threshold dose. Making sure dose limit is well below the threshold dose, you can prevent deterministic effects and minimize the occurrence of probabilistic effects. I'm still not saying prevent. I'm saying we'll try to minimize by keeping the dose as low as possible so that we are at the very close to the origin. If you remember the graph, the dose is low, the probability is low. So this is what we plan to do. That is the intention of dose limits. Now, internationally recommended dose limits for radiation workers and public are adopted in India. Our numbers, if anything, are safer than the limits which are recommended internationally. Now we have Radiation Protection Rules 2004 promulgated by the Parliament of India under Atomic Energy Act 1962. We call it RP or Radiation Protection Rules. They stipulate the requirements for safe work with radiation. That is the role of RPR. And for implementing the provisions of RPR, a competent authority has been appointed under the Atomic Energy Act. In India, the competent authority is Chairman, Atomic Energy Regulatory Board, Mumbai. Now, what is the role of AERB? We have to ensure, this is the mission of AERB, you can find it outside, is to ensure that use of ionizing radiation and nuclear energy in India does not cause undue risk to the health of people and the environment. This is a mission of AERB. AERB functionally issues license to qualified users to work with radiation. And actually, 3 levels of review take place before licensing is given. And then before licensing, AERB consults independent experts. In some cases, major instances, consultation with public is also carried out. This is how AERB carries out this responsibility. To add, AERB specifies safety requirements and also provides guidance to users. These safety requirements and guidance, they are based on IAEA safety standards, that is safety standards published by the International Atomic Energy Agency of the United Nations. We make use of those standards, and by specifying safety requirements and the guidance, international safe practices are referred to, they are adhered to. AERB establishes regulatory procedure for compliance assurance. Compliance assurance is the task of the competent authority. Compliance is the duty of the user. Compliance assurance is the task before the competent authority. So competent authority, AERB, has established regulatory procedure for compliance assurance. These procedures include surveillance of safety status of every institution, big or small, requiring training of personnel and certification of personnel to do the job that they are planning to do. Regulatory inspections are carried out by AERB, and if there is non-compliance, enforcement actions are initiated by AERB. These are the responsibilities of AERB. This is how radiation safety is ensured in India. Now, I have still not answered the question that I asked myself. Is it possible for me to ensure zero dose so that the probability of stochastic effects can be reduced to zero? Now, I know that there is radiation everywhere. The milk that we drink, do we know that contains potassium-40, which is a half-life of 10 billion years, 10 raised to power 10. That's a half-life. The beer we relish contains radioactivity. There is cosmic radiation pounding on us all the time. If you go out of this room, You won't feel it, but you're receiving it. And there is radiation in this room. All of us at this moment are breathing radon. It's not because of Department of Atomic Energy. They've been there all the time. Since the day Earth was born, this has been happening. So there is natural radiation everywhere all the time. And there are risks. So with this, is it possible for us to ensure zero dose? Certainly not. We are getting some dose, something like 2.35 millisievert per year. The number can vary from one country to another. We are getting more than zero dose. So it's not possible to reduce the dose to zero. Now, that time, let us look at risk per se. There is risk in various spheres of life. Look at this small list. Just because there is this risk, have you stopped traveling by motor cars? Just because there is this risk, have you stopped making air travel? Have you stopped using electricity because of this risk? We can minimize the risk, we can try to avoid the risk, but we know risk exists. Or are we hiding in our home because lightning can strike? We are not, because we know the probability is very small. So in any sphere of life, there is an element of risk, and we are accepting it, and we are being wise in accepting this because we know we can get the advantage. Now, I'm just going to make a brief comparison. This is taken from literature. I'm making it brief. Now, smoking 20 cigarettes a day robs a person 2,370 days of his life. Now, person engaged in construction work, he loses 302 days from his life. A person drinking alcohol regularly can lose 130 days in his life. So a person decides, I won't get involved in any activity at all. I will sit at home and idle. What will happen to him? He'll put on weight. This person has 20% obesity. What is his risk? He loses 985 days in his life. That is, whatever you do, whatever you don't do, there is this risk that is existing. So there is no activity which does not pose a risk. So the wise thing to do is to minimize the risk and take advantage of the benefit offered by the technology. Then one word about these dose limits. I want to give a perspective. You can recognize this as the Eiffel Tower of Paris. Its height is about 300 meters. I'm comparing this height with the risk of a 50% lethal dose, about 3,000 to 4,000 millisievert. So I'm just going to quantify various risks. Now I'm going to quantify this something like, say, 1,500 to 2,000 millisievert to this risk of radiation illness like nausea, vomiting, diarrhea, high fever, that kind of thing, infection. So they're pausing symptoms, they're not going to kill. So next, consider this. Now, a person may receive, say, less than 500 millisievert, and maybe 750 to 500 millisievert. He may have symptoms like change in blood picture, etc. Those will not be visible unless we do a blood test. So that compares to the height of a skyscraper. That is the risk if a person gets that much dose. And let us say a person receives less than 100 millisievert. No effect will be detectable. Height of that is equal to the height of a house. That is the risk as compared to height of Eiffel Tower. There is a radiation worker like you and me. He is allowed a maximum of 20 millisievert. Maximum, as you know, can vary can be up to 30 in India, can be up to 50 outside India. But he is allowed on an average 20 millisievert in a year. His height is 2 meters. Compare that with the height of 300 meters. And member of the public, again his height may be 2 meters, but that compares to the height of a brick, 10 centimeters, that's the height. So this gives an idea, gives a perspective of the risk we are accepting when we work with radiation. Now this picture I have taken from an IAEA publication. So this can be accessed in the web. It is an authentic picture which gives you an idea of the risk, a perspective of the risk when you work with radiation. So before I conclude, I just want to draw your attention to the fact that these are the applications that we saw, and this list is not complete. And we can come to a safe conclusion that when used properly, Societal applications of radiation enhance the quality of life. About this, there is no doubt. Now, the last slide is that, look at this picture, X-ray picture. This is the X-ray picture of Mrs. Röntgen. Dr. Röntgen is a scientist who discovered X-ray in the year 1895. This picture was taken on the 22nd December 1895. So people have done a lot of hard work. They have demonstrated to the world the efficacy of X-rays. She has shown her hand. See, this is the use of this technology. So this presentation is dedicated to those whose innovations have enhanced the quality of life. Thank you very much.